Very good morning. Today in this video, we are going to discuss paper part questions for grade 12 advanced physics. So this is grade 12 advanced physics EOT. Let's start with the first question. Apply the equation for illuminance of a point source to numerical problems. Relate luminous intensity to illuminance. So you might be getting questions or problems related to illuminance and luminous intensity. Let's check what are the equations. First one, illuminance can be found by using the formula illuminance E is equal to luminous flux divided by 4 pi r square. And luminous intensity can be found by luminous intensity I equals P divided by 4 pi. And when we get a question, sometimes you might be having confusion what is represented by each letter. So luminous flux is represented by P and its unit is lumen. So in a question, if you are finding it difficult to understand which one is luminous flux, look for the unit LM. If the lumen is given, then you can understand that is luminous flux. Illuminance is represented by the letter E and its unit is lux. So if the question is asking you to write down what is the illuminance, you can use the unit Lx. And luminous intensity is measured in candela. So it is always better to know the units and identify the quantity based on the units. Now, there is a relationship between illuminance and luminous intensity, that illuminance E is equal to I by R square. So sometimes you may be asked to use this equation as well. Let's take a basic example. So here, what is the illuminance on your desktop if it is lit by a 1750 lamp that is 2.50 centimeter 2 centimeter meter above the desk? So they are asking for finding the illuminance. So let's take the equation for illuminance first. And what is this quantity? 1750. They said that the illuminance, if you have got doubt, then you can look for this lumen. Since it is lumen, we can understand that it is P. So P is equal to 1750 lumen. That's given to us. Now, the lamp is 2.5 meters above your desk. So we can say R is equal to 2.50 meter. So plug these values in this equation. Illuminance E is equal to P divided by 4 pi R square. So illuminance E equals 1750 divided by 4 times pi times 2.50 square. So when you do this one, you will be getting the answer. So this is the answer. So I use the equation E is equal to P divided by 4 pi R square. P was given, R was given. So we plug these values into this equation and we got the answer. And as we know that the final answer is illuminance, so we use the unit lux. That's it. Now this is a simple question. Now you may get another one question where you may have to use different formulas. Okay, so this is a screen is placed between two lamps so that they illuminate the screen equally. So they said that the illuminance produced by this one and this one's same. So here we can say that E is same. Lamp 1, this is lamp 1, emits a luminous flux of 2845. So basically we can say this is P1. P1 is equal to 2845 and which is 25 centimeter from the screen. And now the question is, what is the distance of the lamp 2 from the screen if its luminous flux is 5260? So 5260. So what they have given two sources and luminous flux of each source. And these two luminous sources produces same illuminance at the screen. So we can say that illuminance produced by first source E1 must be equal to illuminance produced by the second source. Now we know the equation for illuminance. It is P divided by 4 pi R square. So I can write this is for the first one, it is P1 divided by 4 pi R square equals P2 divided by 4 pi R square, because I am equating the illuminance. So first one is P1. First one's distance, I will take it as R1. Second one's distance of the source from the screen will be taken as R2. So here itself I can cancel 4 and 4, pi and pi. So I can write P1 divided by R1 square. So that is P1 is 2845 divided by 25 square must be equal to 5260 divided by D square or R2 square. So when you solve this one, okay, you can use strip solve method or you can use it manually. You will get the answer. So here, the first one, P1 is equal to 2845, and it is 25 centimeters. Second ones, and R2 is, we don't know. So when you put it in this equation, P1 divided by R1, so we'll be getting R2 is equal to 33.9934 centimeter. Now, the next one was find the luminous intensity of lamp2. We know the luminous intensity can be found by using the equation I is equal to P over 4 pi. P is 5260 divided by 4 pi. When you put in this equation, you got 418.58, which is 419 candela. Candela is the unit of luminous intensity. So the first question for writing part, it's a 10-mark question. It's quite easy. If you know these equations and how to solve this, how to plug the values, if you can understand or if you can identify the values given in the questions, just use these equations so that you get a full score. Now, question number 2, probably 2. And this one is about drawing a ray diagram for a curved mirror and determines the properties of the image. So let's first discuss what are the rays that can be used for drawing a ray diagram in case of a concave mirror or a convex mirror. The first one, we can use a ray. So these rays are known as principal rays. We can use this ray number 1. This is ray number 1, which comes parallel to the principal axis. It comes parallel to the principal axis. After striking on the mirror, it reflects through the focus. So you can use this one, but make sure you draw a line parallel to the principal axis. Then after reflection, it passes through the focus. Okay, this is ray number 1. Ray number 2, the ray which is passing through the principal focus and which is passing through the focus, and then after reflection, it becomes parallel. Exactly opposite of what we have drawn in ray number 1. Ray number 2, passing through the focus. After reflection, it becomes parallel. Ray number 3, a ray which passed through the center of curvature and goes back through the center of curvature. So it goes straight forward and backward, pass through the center of curvature. So whenever we are drawing a ray diagram for a concave or convex mirror, you can use these 3 principal rays. You can use any 2 of it. You don't have to use 3 of them. If you use any 2 of them, that would be enough. Okay, let's check how can we draw a ray diagram for this. This is, you can say that it's a concave mirror and an object is kept here. So I'm going to use the first ray which pass parallel to the principal axis. And after hitting this, what should, how should I draw the second one? It should be passing through the focus. It gets reflected, then pass through the focus. So I draw the first one. Second one, a ray which is coming or passing through the focus and after reflection, it becomes parallel. So I use a blue color for that. It is exactly passing through the focus and then it becomes parallel. So here you can say that these are the 2 rays, reflected rays, and these 2 reflected rays meet at this point, So we get the image in the case of a mirror where these reflected rays meet. Okay, in a mirror, we get the image when reflected rays meet, or when they if they are really meeting, we get a real image. If they are appear to meet, we get a virtual image. Here we could say that a ray coming from the top of this object goes over here, goes over here, goes over. So it comes here. Second ray also coming from the top, it goes here and it comes here. Now I can see that these two rays are coming from the top. So I can say that top of the image will be here. So these rays are coming from the top. So the top of the image will be there. So you should be drawing an image this way. So you get an image this way, and this image, I can say that this is actually, this is formed by the real intersection of reflected rays. So this image is real. And if it is real, I can say that it is inverted. And since it is, if you check this height, and this height, you can say that this image is smaller. This is in case of a concave mirror. How do we draw a ray diagram, or how do we draw a image formation? So depends upon the position of the object, the image is also changed, the size of the image, the orientation of the image, all those things, the position of the image, all those things change. So if the object is at the focus, we get the image, if the object is at the center of curvature, not at the focus, if the object is here, we get the image at the same point. Here we get a same size, and you can see that this is really meeting. These rays are really meeting. The ray go over there and come back. So as they are really meeting, these are real image. And if it's a real image, means it is inverted as well. So this is another one. Okay, so we use reflector, the principal rays, two principal rays to locate the image. And most of the, there are 5 to 6 cases, and in most of the cases, it's same. But when we keep the object in between focus and the mirror, there is a change in drawing. So let's discuss that. So if the object is between the focus and the mirror, let's use the first ray, principal ray, which coming parallel to the principal axis after reflection pass through the focus. Second ray, which is passing through the central curvature and going it back. So that is the second one I use. So when you look over there, these rays are not going to meet anywhere. After reflection, they are not going to meet anywhere here. So not meeting here. But if you look over here, we can see that this is like a converging one. If I trace this backwards, they are going to meet at some point. So we would be getting an image here. So I'm going to trace this one. Let's see. If I want to trace this one, I will be using the dotted lines. Look here. So when you are drawing this one, make sure, whenever you're drawing this one, make sure you use a ruler and trace this line. Like you keep a ruler, keep your ruler like this. Okay, you keep your ruler and trace it backwards, And whenever you're drawing this one, keep your ruler over here and trace it backwards. So look here, just like I trace it backwards. So these two rays, okay, these two rays are meeting at this point. Okay, look here. These two rays are meeting at this point. So I can say the image will be formed over here. Now you can see that these rays are coming from the top of the object here. This is from the top of the object they are coming. So the top of the object will be formed over here. So that's how we can understand that the top is forming here. So we would be getting an image, and this image is upright, because this is upright, and you can see that these rays are not really meeting. These rays from strike on the mirror and they go back, but we feel like they are meeting. So as we feel like we are meeting, we will write it is virtual image. And if it's a virtual image, it is upright, and we can say the size is larger. Okay, so even though we have got six diagrams, and this is a different diagram in concave mirror, so probably this may come for your examination. So when you are drawing, make sure that you keep you keep your ruler straight, and make sure the rays are always passing through the correct point. For example, when you are drawing, make sure that this is passing through the focus and you are tracing that line backwards. Okay, this ray coming parallel to the principal axis after passing through the focus. So make sure it is always passing through the points mentioned. Okay, so this one. Yes. Okay, the next one is about lens formula. Sorry, not lens formula, mirror formula. We have got a mirror formula. 1 by focal length is equal to 1 by xi. xi, this I is for image. So xi is the image position or image distance. We write xo, o is for object, so it is object position, where is the object. So whenever we are taking a concave or convex mirrors, the focal length, there are some sign convention. You need to take focal length positive or negative, depends upon the mirror. For example, in this concave mirror, the light rays are coming over here and all the light rays are meeting here. They are really meeting over here. So here the focal length will be positive. So for a concave mirror, focal length will be positive, because you know that all these rays are meeting here actually. But in the case of a convex mirror, the rays coming over here and rays reflect back. They are not meeting anywhere here. They are not meeting anywhere. They are diverging from it. So there is no chance that these rays can meet. But if you trace it backwards, they meet on the other side. So this is not a real meeting. So this is a virtual one, or this is a fake one. So this focus, we take this as negative. So focal length for convex mirror. If it's a convex mirror, it is going to be negative. All right. And then we can find out the magnification. Magnification M is equal to HI divided by HO, or it can be written as minus XI by XO. So if you have got the magnification M is equal to 1, which means that the image is same size. If M is less than 1, if the M is less than 1, which indicates that the image is small. If M is greater than 1, which indicates that it's a larger one. And we can say that depends upon whether M is positive or negative. We can say whether it's a real image or a vector, real image or a virtual image as well. So let's take an example. Okay. So in this question, a concave mirror has got a radius of curvature of 20 centimeter. First of all, it's a concave mirror, so we can say the focal length is positive. In some of the question, they will give it as positive or negative. If it is not given, it is our responsibility to identify whether it is positive or negative. And a concave mirror has got a radius of curvature 20 centimeter. So R is equal to 20 centimeter. So we can say that F is basically R divided by 2. So this is 20 divided by 2, which is 10 centimeter. You place a 2 centimeter tall object. We can say that object, this is tall. Tall means it is object height. Object height HO is equal to 2 centimeter. So object height, and we can say object height HO and XO. These two will always be positive. So this is object height plus 2 centimeter and object 30 centimeter from the mirror. So I can say that this XO is equal to 30 centimeter. What is the image position and image height? All right, here we use the equation 1 by focal length is equal to 1 by xi plus 1 by xo. 1 by focal length is positive, and that is 10 centimeter. So 1 by 10 equals 1 by xi plus 1 by 30. So as you get this one, you can solve by using your calculator. You get the value of xi. Here you get the value of xi is plus 15. Xi is equal to 15 centimeter. Okay, so we get xi is equal to 15 centimeter. And once you get xi, you can identify the image height. We have got an equation, hi by ho equal minus xi by xo. So here hi is what we don't know, hi. Hi by ho is what is ho? 2. equals minus xi is minus 15 divided by xo is 30 centimeter. So when you plug into the equation, you will get the answer. So let's go to the solved one. Okay, so we have done the from focus is equal to radius by 2. So 20 divided by 2 to 10 centimeters. So we got that. Now we use the equation 1 by f is equal to 1 by xi plus 1 by xo. You substitute and we get the values as 15 centimeter. So as it was a positive one, so we can say xi was positive. So xi was positive means it is always a real image. Okay, xi positive. For a real image, we can say the real image xi will always be positive. For a virtual image, we can say that image distance virtual image will xi will be negative. So here we get xi as positive. So we can say that it's a real image. So if it's a real image, this is going to be upside down. So when you found out mass, so magnification, we got magnification. M is equal to this one. And from that, we found out that image is minus 1.0 centimeter. So since it is minus, I can say it is inverted and its original size was 2 centimeters. So it is smaller. That's a simple one. The next one, convex security mirror in a warehouse has a minus 0.50 meter focal length. A 2 meter tall forklift is 5 meter from the mirror. What are the forklift's image position and image height? So we use the same equation. We use the same equation of 1 by f equals 1 by xi plus 1 by xo. From this one, we understood that its focal length is minus. It's already given minus, so no problem. Otherwise, you need to put minus here. So f is equal to minus 0.50. We know that. And a 2 meter tall forklift. So the height of the forklift is the height of HO equals 2 meter. 5 meter from the mirror. So we can say that this is XO is equal to 5 meter. And we just substitute. So 1 by minus 0.50 equals 1 by XI plus 1 by XO. We know XO. So when you substitute, you get the values. So 1 by X. So 1 by XI. So you get an answer of 0.45 meter. So since the image distance xi is equal to minus 0.45, since this is a minus 1, we can understand that it is going to be a virtual image. If it's a virtual image, we can say it is upright. Okay. So from the magnification, we found that HI is equal to 0.18. So what happened? It was actually 2 meter tall, but it became 0.18. Image is 0.18. So the image is small. So when I get xi is equal to negative from this one, I understand that it's a virtual image. If xi is positive, it's a real image. So here xi, the value of xi is minus, so negative. So I can understand that it's a virtual image. If it's a virtual image, I can understand it's upright. And from height, I got the height of 0.18, but its actual height was 2. So it's small. The next one, calculate the refractive index of a medium by using a mathematical representation. So first of all, we can say the refractive index can be found by using the formula. Refractive index of a medium is equal to speed of light in vacuum divided by, or velocity of light in vacuum divided by velocity of light in that medium. This is the basic equation. So it is a ratio. Refractive index is a ratio. It will give us, how fast or how slow light is traveling in a medium compared to the speed of light in air. So refractive index of a medium like this, and it has got no unit because it's a ratio. Now, next one is Snell's law. So when light passes from one medium to another medium, you can calculate the refractive index by checking the angle. So here you can see the light is moving from first medium N1 to N2. So in the first medium, it produces an angle of theta 1, and the second medium, it produces an angle of theta 2. So I can write N1 sine theta 1 equals N2 sine theta 2. This is Snell's law. Okay, so if you know the values of n1, n2, or if you know the value of n1, then theta 1 and theta 2, you can find out the value of n2. So using this equation, you can uh, identify or you can calculate any missing values. The next one is critical angle. So critical angle and total internal reflection. This one happens when light moves from a medium of high refractive index. It happens only when it is in when the light is moving from high refractive index to a medium with lower refractive index. The light, instead of passing into the next medium, light get reflected back, totally reflected back, which is known as total internal reflection. So here we can see the light enters over here. At a particular angle, light goes like this, making an angle of refraction 90 degree. And this angle is known as critical angle, so which is represented by theta c. And there is a relationship that we can write sine theta c is equal to n2 divided by n1. This one came from this formula because we can say that n1 sine theta 1 equals n2 sine theta 2. If it is moving from this one, I can say that n1 sine theta is what? Sine theta c equals n2. That is a medium, second medium. And we can say that here sine theta 2, second medium has got an angle of refraction is 90. So I can write it as sine 90, but sine 90 is basically 1. From this one, we will get an equation like this. Okay, so the speed of light in air is given. Speed of light in air is 3 times 10 to the power 8 meter per second. The speed of light in a transparent liquid is given as 2.0 times 10 to the power 8. The ray of light incident on the surface of a liquid at an angle of incidence of 40 degree. Calculate the refractive index. So here when we are asked to find out the refractive index of a liquid, we know the refractive index. Refractive index is equal to speed of light in vacuum. Speed of light in vacuum divided by speed of light in that medium. Speed of light in that medium. So this is a very simple question. So as we know that refractive index is equal to 3 times 10 to the power 8, which is the speed of light in air. And the speed of light in this transparent liquid is 2 times 10 to the power 8. So this meter per second, this can cancel, this. So that is going to be 1.5. So speed of light in vacuum or speed of light in air is considered to be almost the same. So you can take 3 times 10 to the power 8. So the refractive index of the medium is going to be 1.5. And since refractive index is a ratio, there is no unit for it. So refractive index is equal to 3 times 10 to the power 8 divided by 2, so 1.5. Now the next one over here. So this one, let's see. We don't get into the details. So let's see that. 4.1 shows a narrow beam of light. Just consider it as beam of light striking on the surface of a parallel side glass block. So this is basically right. We don't have to consider it as a red one. So that's a mistake from my side. I forgot to erase it. Okay. So 4.1 shows the narrow beam of light striking the surface of a parallel sided glass block. So what happens to the speed, to frequency, and to the wavelength of light as it enters a block? So we can say that light is traveling from one medium. Maybe I can say this is from air and this is to glass. So as the light is passing from one medium to another medium at an angle of incidence, at an angle of incidence, this will be refracted. And during refraction, we can say the speed changes. Okay, speed changes. Here, whenever there's a refraction happens, or whenever it moves from one medium to another medium of a different refractive index, there's a change in the speed. Here, what happens? I can say that if it is from air to glass, its speed reduced, speed decreases. But whenever there is a change, refraction happens, the frequency always remains constant. Frequency is the property of a source. For example, when I talk, my sound, my frequency, my frequency is the frequency which I produced. But my sound may be going in different through different medium. Maybe it is going through a wood, or maybe it going through air or water. So the frequency is independent of the wave. So here we can say that frequency remains constant. Okay, during a refraction, frequency will remains constant. So now the wavelength changes. Wavelength change depends upon the speed. If the speed increases, wavelength will increase. If the speed decreases, wavelength will decrease. So here, if it is from air to glass, the speed of the light decreases. So speed decreases means wavelength also decreases. Now calculate the refractive index of the glass. So here we can use the formula n1 sine theta 1 equals n2 sine theta 2. So here we can say that n1 sine theta 1 is equal to n2 sine theta 2. So the first medium, I can say the first medium, this refractive index of refractive index of air n is equal to 1 and 2. So here, when you put in substitute in this one, we get the refractive index of 1.41. So same equation, n1 sine theta 1 equals n2 sine theta 2. So I consider this one as n1, and n1 is equal to 1, n2 is equal to dash. So 1 sine 45 equals n2 sine 30. So n2 equals sine 45 divided by sine 30. So when you plug these values in the calculator, you get, let's see, sine 45 divided by sine 30. You get it as root 2, which is 1.41. Done. Now the next one is about the critical angle one. So here also we can see it shows a ray of light. The ray passes. Okay, so the light goes from glass to air. So it is from a higher refractive index medium to a lower index refractive medium. So at this particular angle of 40, it passed through this one. The angle of refraction is 90 degree over here. So state the name given to the angle of incidence marked 40. So here we can say that at this particular angle, the angle of refraction become 90. So this is known as critical angle. Now they are asking calculate the refractive index of the glass. So here also I can say this is medium 1 N1 and this is medium 2 N2. You can use the equations n1 sine theta 1 equals n2 sine theta 2. So n1 is n1 sine 40 equals n2 times sine 90, because it is angle of refraction is going to be 90 degree for a critical angle. So n1 is equal to n1 sine 40 equals n2, which is 1. So n1 is equal to 1 by sine 40. So 1 divided by sine 40. So you get it as 1.56. Okay, so here it's a critical angle n1 sine theta 1 is equal to n2 sine theta 2. So here you need to take the theta 2 as 90. That's the only thing. Okay, the next one is drawing the image formation on a convex lens and concave lens. So in the case of convex and concave lens, we have got some ray diagrams. Let's study the first one. So principal rays, ray number one, which is coming parallel to the principal axis, and after refraction, it passed through the focus. So here in concave or convex mirror, reflection happens, but in concave or convex lenses, refraction happens. So the ray coming parallel to the principal axis after refraction passed through the focus. This is the first one. Second one, the ray which is passing through the focus, as after refraction, it becomes parallel. Third one, the ray which is passing through the center of the lens undeviated without any refraction. So that these are the three principal rays we can use for drawing. So this you can use any two from these principal rays. Okay, let's see how to draw image formation. So here we can see that an object is kept between 2F and F. So I use the first ray which passed coming parallel to the principal axis after refraction passing through the focus. I use the second one which is passing through the focus, then it becomes parallel. These two are meeting at this point, these two are meeting at this point. So image will be formed over here. Since these two rays are coming from the top, I can say that the top will be formed over here. So we can draw the image. From this one, we can understand that the image formed over here is real because they are really meeting, and the image formed is upside inverted, and the image formed is larger. So there are many other ones, many other formation, but I think this is different from other things. So let's draw this. How to draw image formation when the object is between the focus and the lens in case of a convex lens. The first one, ray coming parallel to the principal axis after refraction, which passed through the focus. Second one, the ray which is passing through the center of the lens without deviation, and there is no chance that these two are going to meet over here. So I will have to trace it backwards. So I just traced it backwards, and both of them met at this point. And these two are from the top, the refracted rays. These two are from the top. So the top of the image will be formed over here. So we would be drawing it in this way. So here we can say that image formed is virtual because they are not real. It's a virtual one, and if it is virtual, it is upright, and then here it is larger. So in this case, we can say that here the lens, this is where we use, if whenever we are using the convex lens as a magnifying glass, we always keep the object between the focus and the convex lens. So this is, if they are asking you to draw the image formation for a convex lens as a magnifying glass, this is the diagram which you need to draw, because whenever we are using it as a magnifying glass, we keep the object between the focus and the lens so that we get a virtual image, enlarged virtual image. Okay, so this one also. These are some of the other diagrams. Now let's check how can we draw image formed on a concave lens. So this one, the first ray which is coming parallel to the principal axis, after refraction, it goes away, like it's diverging. Actually, after coming over here, it goes away. But when we trace it back, we will feel like this is coming from a point in the focus. So that is the first ray. So you should draw this one, and then you should draw the refracted ray over here. Then you will have to trace it backwards. When you trace it backwards, it should pass through the focus. Or else what you need to do is, after coming here, you should keep your ruler like this and draw a line. So when you trace it backwards, you need to do the dotted lines. Okay. Now the second ray, which is coming from the top of the object and passing through the center of the lens. So these two are meeting at this point. You can see that these two are from the top of the object. So the image, top of the image will be formed over here. So we get an image. This image is virtual because they are not formed by the real interception. They are virtual, and we can say the small, since it is virtual, it is going to be upright. Okay, that's it. Now the next one is thin lens formula. We may have to probe solvents by using this thin lens formula. When we use this formula, you will have to make sure you choose the focal length or image distance, object distance, those things correctly. Like they have got sign convention. For example, let's see here, in the case of a convex lens, all the light rays meet over here. So they are really meeting. So they are really meeting. So we call the focus or focal length is positive here. When they are really meeting, focal length is positive. But in the case of a concave lens, the light rays diverge, and when we trace it back, they are meeting at a focus here. So in the case of a concave lens, focal length is negative. Negative. Now, XO means the object distance. Object distance is always positive. For mirror or lenses, in lens, XO is always positive. And HO, height of the object, is always considered as positive. Now, if you want to make a conclusion, we can say that for XO is always positive, HO is always positive, then we can say that for real images, if the image is real, then we can say that it is always positive. For a real image, XI is positive. Very important. For all real images, XI will be positive. And for all virtual images, XI will be negative. Negative. So when we talk about this one, in the case of a concave, in the case of a convex lens, we can say that the Xi will be negative only in one case. And in the case of a concave lens, in the case of this lens, Xi will always be negative. So let's do a question. So now an object is placed 30 centimeter in front of a converging lens and then 12.5 centimeter in front of a diverging lens. Both the lenses have a focal length of 10 centimeter. For both cases, find the image distance and the magnification. So first of all, we can say we have got one equation, 1 by f is equal to 1 by xi plus 1 by x. So this is the equation. And we can say this is a converging lens. So the focal length will be positive. So f is equal to plus 10 and XO is equal to plus 30. And we need to first of all find xi. So 1 by 10 equals 1 by xi plus 1 by 30. So from this one, you would be able to get xi. So you will get the value of xi. How much is the value of xi? So xi, we will be getting xi as plus 15. Okay, once we get xi is equal to plus 15, then we can say the magnification m is equal to hi by ho, which is equal to minus xi by xo. So if you put it in this equation, hi divided by ho is what? How much is the ho? An object of 30 centimeter in front of a converging lens of 12.5 in front of a diverging lens. Okay, so both the lenses, both cases image distance. Okay, so that is not given. But are they asking us? Okay, they are just asking us the image distance only. So we got the image distance and the magnification we can find out by, so magnification we can find out by using minus xi by xo. minus xi is minus 15 divided by 13. So you get a value of m is equal to minus 0.5. So we use the same thing here, minus 0.5. As m is minus negative, then I can say that this is m is negative, magnification is negative, and so it is real. Real. So because minus 0.5 is, since it is 0.5, I can say it is very small. So I use the same equation over here. I put in the equation. So I got a value of plus 0.44. So m is positive and less than 1. Since m is positive, we can say it's a virtual image. Not that one, but we can say here, don't get confused. Okay, so this one, xi value, we got xi value over here. Then m is equal to 0.44. As we get m is equal to 0.44, I can say that it is less than 1. So it's a small image. At the same time, we can say it is positive. Positive means we will be getting it as a virtual image. Okay. So that's what all for this. Thank you so much. All the best for the exams. Make sure you guys learn how to draw the ray diagrams correctly and taking the sign convention correct for mirror equation and thin lens formula. So that's what. Thank you so much.